Hello everyone, my name is Jafari and I would like to welcome you to another video of the data mining series. In this video, we are going to talk about and get deeper into numerosity data reduction. We're going to look at a few methods and talk a little bit about each of them and their applications and where do they stand in this whole data pre-processing and data mining concepts that we are discussing. All right, let's get to the slides. All right, so in this slide, we're going to cover these items. Of course, we're going to talk about what is numerosity data reduction, and we are going to compare that with dimensionality data reduction so we understand it better. And then we're going to look at three types of numerosity data reduction: random sampling, stratified sampling, and random over or undersampling. So let's get to it. So as we discussed, there are two types of data reduction. Numerosity data reduction, when we focus our efforts to reduce the size of data to the number of rows, as in when we reduce the data, the output or the end result of the data reduction is going to have less number of rows, as opposed to dimensionality data reduction, which is when we put our effort to reduce the size of data, we're going to end up with less number of columns or attributes. So that's a big difference, and that's what numerosity data reduction is, and us trying to have less number of rows in the reduced data set. So the first method is random sampling. Random sampling, as sort of shown in this figure, is the idea of selecting less than the number of the data objects that are in your data set to reduce the number of data objects in your sample. And most of the time this is used in cases that we are interested in sort of cutting cost, cutting computational cost. In a lot of cases that we are interested in cutting computational cost are specifically shown in the developmental stages of machine learning algorithms. There are a lot of experimentations goes into tuning and finding the best set of attributes and a lot of other things that in those developmental stage it would speed along things if we were able to have a less computationally expensive processes. And one of the things that can be done is in those stages use a sample of the data set, so we can sort of like fine-tune the methods and the algorithms using the sample, and then when we are ready to actually train the model that's going to be used for decision making, now we can use the whole data set. Of course, sometimes this random sampling could be used as a way to reduce the size that we're going to use for training that is going to be used for decision making eventually. So that's the applications of random sampling. So let's move to stratified sampling. Stratified sampling is very similar to random sampling with only one difference. Of course, both of them are random sampling. I mean, you are going to have random samples. But with the stratified sampling, it is important for us to make sure that the ratios of the subpopulation in the data set that are important to us are maintained. So let me try to explain that in this example. So here in the middle, we have a data set, right? So this is our original data set. You see, this is our original data set. And here we have taken 10 samples. The ones on the right are random samples. The one on the left are stratified sample. Pay attention here. We have in this data set, the original data set, we have 6 stars and we have 24 plus signs, right? So when we do random sampling, we don't care about how many star signs and how many plus signs we have in this data, and we just do this randomly, and as a result sometimes we get 2 stars, sometimes we get 4 stars, sometimes we get 3 stars. But stratified sampling says that it is important for me to have the same ratio between the important subpopulations in my data set. So imagine that being star and being plus is important. So we do stratified sampling to make sure that the ratio between these two subpopulations are the same. To keep that ratio the same, when we are sampling 15 out of 30 data objects, we have to always make sure that we get 3 stars and 12 plus signs. And this is to just make sure that the ratios of the the subpopulations and data sets are maintained. So now let me ask you this question. So when we do stratified sampling over random sampling, when we are doing this, are we basically changing the chances of data objects to be selected or not? In other words, when we do stratified sampling, the subpopulation with less number of data objects, does this mean that they have higher chance of being selected? So this is important because, as you remember, when we discussed data reduction goals, 2 of the goals that we had was, 1, to make sure that we have a smaller version of the data. Well, either these 2 sampling does that. The second goal was to make sure that we maintain the integrity of the data. If stratified sampling gives a higher chance to a part of the population, then we'll start to be worried about having maintained the integrity of the data. So I encourage you to, if you're watching this video, provide an answer to this question in the comments, and after a while I will also provide that answer eventually. So the question is, are we changing the chances of data objects being selected by moving from random sampling to stratified sampling or not, and why? Alright, so let's move on to the next method, random over/undersampling. So here specifically, actually, we end up giving more chance to some data objects over the others. The reason is because our analytics need wanted us to do that. So basically, by oversampling, we give higher chance to some of the data objects and we give lower chance to other data objects, which is the undersampling. So let's look at the difference between oversampling, undersampling, and the stratified sampling. So this is a case study of being able to classify between non-churning and churning customers based on their subscription length and frequency of their SMS or text messages. So we do see here that if we were to do stratified sampling, we would maintain the ratio of churn over non-churn. Here we have roughly around 20% churn and 80% non-churn, right? So 0 and 1 specifies that, and this has been carried over in this area. But due to some analytical goals, which most of the time is because we want our classification algorithms to have the same chance of learning from churn cases or non-churn cases, the cases that are less frequent, we say, okay, I want to randomly take a sample, but at the same time I want to make sure that my sample is a 50% representation for churn and non-churn, right? So when we have such a prescribed ratio, we want to basically inflict on our data and get a sample like that, we are basically using, sort of like changing this randomization, controlling it in a way that the data objects that are less frequent have more chances of being selected. Just because, our analytic goals tells us that that would be better. I mean, in some cases. So let's take a look at the goals of data reduction when we have random or random over or undersampling. Are we really standing by the objectives of data reductions as we discussed? Of course, we are obtaining a reduced representation of the data, but are we really maintaining the integrity of the data objects? We are not. We're actually changing the ratios of our subpopulations intentionally, and that is done for analytic purposes. In fact, what is really happening here that we are seeing is that we are basically mixing data transformation and data reduction here, right? Oversampling and undersampling, in their essence, they are data transformation tools, right? So we might actually end up repeating some data objects because they are so infrequent that our algorithms need to see them. So when we get to a point that we have to do some data reduction at the same time, our algorithm needs a prescribed ratio between the subpopulations, then we basically mix these two steps, and that's why here this method, random over undersampling, is not really maintaining the integrity of the data. And that doesn't mean that that's a bad thing. It's a good thing, because we are doing that part to change these ratios as the data transformation part. And random over undersampling, it's only a data reduction when it is mixed with data transformation. We never have a random over undersampling just as a data reduction. That's only when this mix happens. So let's use this opportunity to learn a little bit about the difference between data transformation and data reduction. Data transformation is when we actually inflict change. Basically, we change the integrity of the data. We move the data. We have different values because the data analytic goals requires them, or our data analytics will become successful for those matters. But data reduction, our only goal is to reduce the size of the data. At the same time, we don't want to lose the integrity of the data. As we did see in a lot of examples, we have to mix data reduction with data transformation, like the examples that we saw here. And in those cases, you have to understand that because of those mixing that you're doing, you are not following the data reductions to objectives. So before finishing this video, let me offer you a quick summary. In this video, we talked about numerosity data reductions, and we specifically talked about random sampling, stratified sampling, and random over / undersampling, and we saw a couple of examples and the differences between them. Until the next video.